Hi again. Well, we're going to be looking at the beginning of this with the SVT diagrams. And for that, we're going to need a constant acceleration, like here on Earth. For example, if you drop a ball, what happens? And how does the position change? We'll naturally take the position graph first. So let's just get started here. On the left, you see what's normally in the y-axis. That is going to be our position. And on the x-axis, that's time. And that's pretty standard. So the position will change, say, when we drop a ball due to gravity, which is constant. And it is, well, you're used to it, 9.82 meters per second. We'll just leave it as g. If we were dealing with a different acceleration, we would have an a there for the general acceleration, but I said we're going to be looking at things here on Earth. So now you can see that this is a second degree function, that the longer you go, the greater the distance goes, and it goes pretty fast. That every second interval is going to give you more distance than what you had before the previous second. So we expect it to grow like that. Now, I want you to think back to calculus or Math C, and what happens to second degree equations when we take the derivative of it. And in this case, since it's kind of applied to this scenario, if you're taking the derivative of a distance function, what will that do and what will you get? And remember that the derivative at any given point, you're going to get a tangent line, and that tangent will have a slope, and that slope represents something. So think in your mind for just a little second here, and we'll take the next one. There we go. The derivative of the position function will give you the velocity. Okay. Not surprising. I know we've talked about it before, even discussed it, but now it's time to remember this and be able to use it, because you're going to need to be able to take the derivative of things and be able to apply it to something. And there will be a lot more functions, and the problems will start getting more difficult now that this is the second year of physics. So, all right, with the velocity, we're going to get, again, here it's here on Earth, so we have constant acceleration. We would expect, and we know from experience, that when you drop a ball, at first it's not moving too fast. It just leaves your hand, and it picks up speed and picks up more and more speed until it hits the ground. And that's what we're going to get here. Now, obviously, we don't always have to just think of it as dropping a ball. It can be a car accelerating or whatever. If we now take the derivative of this, what do you think we're going to get? It's related to what we just did. So remember back, if you take the derivative of a linear function, do you remember what we talked about? That you get, since it's a line, it's just the k value wherever you are on that line. And that's what we're going to get. We will get the acceleration. And here on Earth, of course, that's g, and that's about 9.8 meters per second squared. So now let's continue, because now we know what the S, V, and T diagrams are and how they're related to one another. So let's look at one of the things we have in the book. This is a position formula, and here, unlike what we started with, like there that was, see, that's similar, but it's not exactly the same. They've added this, and that's because you don't have to have 0 as a starting velocity. Maybe you're throwing the ball straight down, perhaps off a building or something. Then it would have an initial velocity, and then it would pick up even more speed based, or more distance, since that's what we're talking about. But of course it would increase its speed, and that would increase its distance even faster. All right, now let's look at the velocity ones. The first one we looked at, that was this one. But again, you may start off with an initial velocity. The increase for constant acceleration would still be linear. It's just that it would be shifted upwards to whatever you started off with, like right there. So not so strange. We will be doing problems that deal with both scenarios. We probably won't do too many graphs with that, but we may solve physics problems with them. The graphs will be very often with velocity, and we'll sometimes need to interpret them. So, okay, that's what we had for this time. Thanks for watching. See you next time.